Hey, you're on the Tutor Hotline with Melissa Maribel. How can I help you?
Hi Melissa, I need help on question 11 and number 12. One asking for the percent yield and one asking for the theoretical yield. Thank you.
Okay, let's go over that. So this question says the combustion of 0.374 kilograms of methane in the presence of excess oxygen produces this amount of carbon dioxide. What is the percent yield? So let's just start off with identifying what are we given and what are we finding. So, okay, what are we given? Well, we're given two different values. So I know that we have this amount for methane. By the way, what methane actually is, it's CH4. And then it says for the presence of excess oxygen, but that doesn't tell me how much of oxygen we have. It produces this amount of carbon dioxide. So I know that, well, because it produces carbon dioxide must be our product since it's being produced. So, okay, I know that much. Now, what does that really tell me though? Well, one, I know I'm also looking for the percent yield. Now for the percent yield, we're going to need something known as the actual yield and the theoretical yield. So these are all the steps that we're going to talk about and go through. We're going to start off with writing the balanced equation. Then we're going to find the theoretical yield by doing a bit of stoichiometry. And then lastly, we'll find the percent yield. So I'm going to start off with just writing the balanced equation. Now, there's several hints in this question. One, you do have to know what methane is. It's CH4. So since I know, okay, that's methane, CH4, and plus this is telling me there's an excess of oxygen, and it produces carbon dioxide, all of these are hints. The other huge hint is just the fact that it says it's combustion. If it's combustion, well, I now know the type of reaction it is, and I know all the different things that are going to be part of this equation. So in a combustion reaction, recall that we're going to have something known as a hydrocarbon. What a hydrocarbon is, it's just a molecule that consists of only hydrogens and carbons. So that's our methane in this case. And what never changes is your reactant and your products. So you're always going to react this with O2. That's the excess O, or oxygen, right? O2. And then oxygen will not exist just by itself. It's a type of diatomic molecule, meaning it exists in pairs. So that's why we have that O2. Next, it's going to produce carbon dioxide and also water, just because this is a typical combustion reaction. So as I mentioned, this never changes. This part never changes. The only thing that changes is the hydrocarbon that you're initially given with. So in this case, I know that I'm going to start off with our methane that's provided. I'm reacting that with the excess oxygen, so O2, and we'll produce carbon dioxide and water. So now that we have that, let's just balance this out. So what I like to do with balancing is just write out every single element individually on either side for our reactants and our products, and I'm going to identify how many of each element we have on either side, on the left side, which is the reactants, and the product side, which is the right side, which is the product side. So in this case, I have one carbon on the left side, or the reactant side. And then for hydrogens, I have 4, right? Because of this subscript, I know that I have 4. Next, for oxygen, the subscript tells me there are 2 oxygens on the left. I'll do the same thing for the product side. So looking here, there's only 1 carbon. So 1 carbon. Next, for hydrogen, there's 2 due to the subscript. So 2 hydrogens. And beware of your oxygen here. Some people may say, okay, there's only 2 oxygen. That would be wrong, because don't forget about this other oxygen. So we have 2 plus this additional oxygen, so there's actually 3. So 3 oxygens. Okay, so just a rule of thumb for balancing, always leave oxygen to the very end, because it tends to kind of work itself out or get a little bit confusing if you start there. So I'd say start off with anything other than oxygen. So I would typically start off with carbon. However, carbon in this case is balanced already. So now I'm going to move on to hydrogen. So okay, I need 2 more here, right? Because this is 4 and this is 2. So I'm actually going to place a 2 in front so it can then multiply with that hydrogen and become 4. So that's exactly what I'm going to do. I'll place a 2 in front. Now when I do that, it's like I'm distributing now this 2 into the hydrogen and to the oxygen. So I know, well, the amount of carbons didn't change because I didn't place anything in front of this carbon. So I know carbon is still 1, but the amount of hydrogens does change because I multiplied 2 times 2, which now gives me 4. Our oxygen will also change because we have 2 times, well, 1, since there's no subscript there really, so 2, but that's not it because I still have an additional 2 here, so 2 plus 2 gives us 4. So now we have 4 oxygens. Okay, so now that we have this, the last thing we have to do is just balance out our oxygens. So let's keep going. So then now I'm going to look back here and say, well, what number do I have to place here to multiply with this 2 subscript to give me 4? Well, 2 times 2. So I'll place a 2 here. These 2 would then multiply, and that's going to give me 4 oxygens, while nothing changes for carbon since I didn't place anything in front of CH4. And then nothing changes for hydrogen since, once again, I didn't place anything in front of CH4. So now that we have our balanced equation, let's go to step 2, which is finding the theoretical yield. All right, so with this type of question, I know to find the theoretical yield because, well, one, it's telling me to find the percent yield, and the formula for the percent yield is actual yield divided by the theoretical yield, so I need it. Now, the theoretical yield is found by, well, identifying the limiting reactant. And in this question, they actually tell you what the limiting reactant is already because they tell you what's going to be produced. So they only give you one amount of our reactant. They don't tell you the amount for O2. Plus, they tell you that O2 is actually your excess reactant by just stating excess. Now, if you need to figure out or need to go over how to find the limiting reactant, I do have a video on that. You can find that right here. So definitely refresh your memory because that is really important with this question. So continuing on with just finding the theoretical yield, what I'm going to do is I'm only going to do this once since I'm looking for the theoretical yield specifically of the limiting reactant, which is methane. Well, I'm going to go from grams of my reactant to then grams of my product, which is carbon dioxide. Right? Because this is our actual yield, I need the theoretical yield of the same product, which is carbon dioxide. But we have an additional step just because I'm not starting with grams, I'm starting with kilograms. So that's actually what I have to start off with. I have to start with converting kilograms of methane to grams of methane by using the metric system. And then from grams of methane, I have to find my way to grams of our product or grams of CO2. If you don't know how to do that, once again, this is stoichiometry. Well, how you're going to do that is you're just going to convert to moles. Whenever you're not sure what to convert to, typically like 99% of the time, moles is going to be your best bet since all of the conversion factors equal moles. Okay, not in this case for kilograms, but at least when we're starting with grams. So what I'm going to do is I'm going to convert to moles in this case. So I'm going to convert to moles. And then now, since I'm at moles of methane, I want to do a mole-to-mole ratio to then get the moles of CO2, which is our product. So this just allows us to change the compound that we're looking at. And then finally, I want to get back to grams, and I'll use the molar mass in this case to get back down to CO2, so grams of CO2. So this is our plant. Now I'm going to keep going, and let's just put everything together and do the math. So starting off with the kilograms that we were given initially, this is the amount of kilograms I have for methane. Now what I'm going to do is I'm going to just convert this to grams. So this is our first step. What I'm going to use is the metric system. So the metric system tells us that 1 kilogram is equal to 1,000 grams. So okay, I know that. Now all I have to do is multiply. So these two would then cancel. So let's show that. These two cancel. And then now I'm at grams of methane. Now that I'm at grams of methane, I can then move forward to go to moles of methane. How I go from grams to moles is by using the molar mass of methane. So I know I'm going to use this molar mass. And remember how to find molar mass, all we're doing is looking at the individual masses of every single element in this compound and then adding them together. So carbon is 12.01, and then hydrogen is 1.01, but there's 4 of them, so I'll multiply that by 4, and I get this. Then I'll add these two values together to get this as our molar mass. So what I'm going to do is just align the units so they can cancel. So these two units are aligned across from each other. So I know that those grams and grams of methane would then cancel, and that brings me to moles of methane. So I'm here. So now that I'm here, I'm now going to move on to do a mole-to-mole ratio to get the moles of carbon dioxide. So like I said, a mole-to-mole ratio is going to take place here. That's what allows you to go from moles of one compound to moles of a completely different compound. What I have to do is use the coefficients. So I'm looking at the balanced equation, and I'm looking at the coefficients involved in our balanced equation. So it'll make sense once we do this. So what I'm looking at is, looking at this balanced equation, there's really a 1 here. So there's technically a 1 right here, and there's a 1 right here if there's no other number that's being shown. So then I know, well, there's 1 mole of methane, and I'll align the units again so they can cancel. So so those cancel. And then for every 1 mole of CO2, so that's on top. Now that I'm at moles of CO2, I can then convert this to grams of CO2 by using the molar mass of CO2. So once again, finding the molar mass, I'm just adding this together. So then this is carbon, 12.01, oxygen, and then I did multiply 16 times 2, just a little note. So that's how I got that 32, so multiply that by 2. And then add these two values together, and this is our molar mass for carbon dioxide, and I'll place that here. So we're multiplying by it. I know that we're multiplying by it because we're aligning, once again, the units across from each other so they can cancel. So that's how you know where to place everything. And then from here, almost done, I'm now going to multiply all of this together. So I'd multiply everything right across, and then I divide by that 16.05. When I do that, I get this value. But I always have to worry about my sig figs. So in this case, looking at what we initially were given, we were only given 3 significant figures, so I have to round to 3 sig figs. So I'm going to round up to this. And remember, this is 3 sig figs because anything that doesn't have a decimal, it's a large number without a decimal, those ending zeros do not matter. So I only have 3 sig figs in this case, that 1, this 0, and 3. So this is my theoretical yield. Okay, we found the theoretical yield. Now let's find our percent yield. Because we have our actual yield and we have our theoretical yield, what we now have to do is plug this into our formula. And even before then, I would say, beware of this. Look at our units. Our units are not the same, right? So this is kilograms and this is grams. What we want to do is we always want to have the same units. I could either convert these grams to kilograms, or I can convert these kilograms to grams. Either way, it gives you the same result. So what I'm going to do is I'm going to convert this back down to kilograms. And all I'm going to do is just, using the metric system again, I'm going to divide by 1,000, and that's going to give me this amount of kilograms. So okay, I have my kilograms now. Now that both of these are in the proper unit, the same unit, then I can continue. So our percent yield formula is our actual yield divided by the theoretical yield, and multiply that by 100 since it is a percentage. If you forget this, which please don't forget this, all you have to think of is percent yield, it's where it's at. All right, so where it's at, that's percent yield. So that's just a nice way to be able to remember this, just in case you forget this on your exam. So all we have to do now is plug everything in. So I'm going to plug in the actual yield, which was given, and then I'll plug in the theoretical yield, which we found using stoichiometry. Divide these two values and multiply by 1,000, and we get 95.4%. That is our percent yield. Let's move on to the next question that asks for theoretical yield. All right, so this question states the combustion of 0.1240 kilograms of propane in the presence of excess oxygen produces this amount of carbon dioxide. What is the theoretical yield? So it's really similar to the previous one that we just did. Let's once again identify what are we given and what are we finding. So we are given this amount of propane, and propane, that's one to know, propane is C3H8. And then we are given, again, how much product we are producing. So we are given our actual yield. Is it relevant? Do we even need our actual yield? Nope. So this is extra information. There's no need to even use it in this case because we're not asked to find the percent yield. So because we're not asked to find the percent yield, the actual yield isn't necessary in this question. So instead, all I'm using is just the amount of kilograms of our reactant or of propane. And then of course, what I'm finding is our theoretical yield. The steps that we're going to take to find our theoretical yield are as follows. All we have to do is figure out the balanced equation and then find the theoretical yield with using stoichiometry like we did previously. So let's start off with our balanced equation. Once again, this is a combustion reaction. So that means that the only thing that changes is this hydrocarbon, and everything else remains the same where we're adding O2, that's our excess oxygen. And then it produces that carbon dioxide and water. So doing this all over again, just balancing this out, remember we're going to write all of the elements on either side and figure out how many of each element we have on either side and then balance them out. So looking at carbon on this side, we only have 3 due to the subscript. So I have 3 carbons. Next, looking at hydrogen, there's 8. So 8 hydrogens, and oxygen, there's 2. All right, looking at our product side, carbon, there's only 1 carbon here. For, let's see, hydrogen, there's 2 because of that subscript. And then oxygen, remember, there's actually 3 because we have 2 plus this 1, so 3 oxygens. Always start off with, I'd say, anything that's other than hydrogen or oxygen. Always leave oxygen to the very end because it makes it a lot easier. So I'm going to start off with carbon. So carbon, there's 3 carbons here and there's 1 carbon there. So I'm going to place a 3 here so I can turn this carbon into a 3. So when I place a 3 coefficient there, what's actually happening is this is distributing. So this 3 is being multiplied to this carbon, this 3 is being multiplied to that oxygen. So we now have 3 carbons, and we have 3 times this 2 subscript, we have 6 oxygens. But don't forget, we don't have 6. We have 1 more, so beware of that. So 3 times that 2, 6 plus 1 more. So I'd say, don't just look at one side, keep looking at like, oh, what else is this added to? Is there any other oxygens hidden there? And there are. So we have 7. So we have 7 oxygens. Now hydrogen, nothing changed because we didn't put anything in front of hydrogen, so that's going to remain the same as 2. So now that our carbons are balanced, I'm now going to move on to hydrogen. So there's 8 hydrogen here and there's 2 on the product side. So I have to multiply a number here to 2 to give me 8, and that's 4. So I know 4 will be placed there. Once again, I'm distributing this. So distribute, and then so 4 times 2 gives me 8. So now I change my amount of hydrogen, so that's 8. And then the amount of oxygen will also change. So we have 4 here, and then plus the additional 6 here. So 6 plus 4 is 10. So I have 10 oxygens, and nothing changed with carbon. I didn't change this number, so that's going to remain the same as 3. Okay, so almost there. Now we're finally balanced with carbon and hydrogen. Now our oxygen is the last thing. So I have to place some sort of value here to multiply with 2 to give me 10. So 5 times 2 will give me 10. So I'll place a 5, and then from here, this is now 10, and everything is balanced since I didn't change anything on this carbon or anything to this hydrogen either. So this is our balanced equation. Continuing on, our next step is to simply find the theoretical yield. So this is really similar to the previous question with finding the theoretical yield. It's pretty much the same exact way of doing this, where I'm going to convert the kilograms to grams. Now, after I use the metric system, of course, to go from kilograms to grams, I'm then going to use the molar mass of propane and convert this from grams to then moles. Then continuing on with moles, I now have to change the compound, so I have to do a mole-to-mole ratio, and that'll bring me to moles of carbon dioxide. And lastly, I want to convert this to grams of carbon dioxide, so I'll use the molar mass of carbon dioxide to get to grams of carbon dioxide. So the theoretical yield, I know, is whatever the limiting reactant produces. Our limiting reactant in this case, because it really tells us, is propane, since our excess reactant, hint, hint, excess, is oxygen, okay, is that O2. So, okay, I know that since that's given, I don't have to do this twice, and let's keep going with this. So I'm just going to put this all together. So starting off with what we're initially given, the kilograms of propane, and I want to convert this to grams. So once again, I'm going to convert this to grams, and I'm just using the metric system, which was that 1 kilogram is equal to 1,000 grams. Aligning our units across from each other so they can cancel. So this cancels. We're now at grams of propane, so I'm here. Next, I want to move on to moles of propane. How do I go from grams to moles? I use the molar mass. So I need to find the molar mass of propane, which is what I did here, multiplying that 12.01 times the 3 subscript to give us this. And then, of course, multiplying 1.01 times that 8 subscript to give us this. Add these two values together, and 44.11 is our molar mass of propane. So, of course, once again, I want to align the units so they can cancel. So these 2 grams across from each other so they can cancel out. And I'm now at moles of propane. So I'm here at this step. Now I want to change the compound. So when I want to change the compound, I'm going to use a mole-to-mole ratio, which is found using our balanced equation. Okay, I want to align my units so they can cancel. And remember, if we don't have a coefficient in front, then assume that it's just 1. So in this case, I know that for 1 mole of propane, which I'll align the units so they can cancel, there's 3 moles of carbon dioxide, which is on top. So our units of moles of propane will cancel. And then next, I'm here, so I just have to convert this to grams of carbon dioxide by using the molar mass. So remember, molar mass allows us to go from grams to moles or vice versa, moles to grams. So then identifying the molar mass of carbon dioxide, we did that previously. And all I have to do is then align the units again so they can cancel. Moles of carbon dioxide are on the bottom. Those would then cancel out to get grams of carbon dioxide, and we're just going to multiply everything on top, so all of these out, and then divide it by that 44.11, and it's going to give us this value. We could stop here. That would still be correct. But because they gave us the amount of kilograms, or the amount of kilograms in general, right? Everything was initially in kilograms. They most likely want the answer to remain in kilograms. So I'm going to convert this back down to kilograms. And all I have to do is, using that metric system again, right, this conversion factor, is align those units across so they can cancel. So I'm dividing by 1,000, and then that's going to give me this amount of kilograms overall. So this is my theoretical yield. This question is a common test question and a finals exam question. Yeah, I know. So make sure to study these types of questions, anything talking about percent yield, theoretical yield, limiting reactants. All of that is the most common final exam question. Now, if you have other questions and you want the answers to them and want to figure out what am I doing, please ask me. Simple as that. So in the description box, you'll find a link and you could submit your question and I'll be happy to answer it. And I'll see you in the next video.